Hi, I'm David Patterson. I'm a retired research scientist. I have a degree in applied maths and a PhD in engineering. I want to apologise up front for the poor quality of this talk. There are at least 15 different systems of infinite numbers that have been invented by mathematicians over the years. Most people know only one. Most mathematicians know only two. In giving this talk, I'm condensing each system of infinite numbers onto a single slide, which is really nowhere near enough room. And also I'm rushing through the presentation to keep the total presentation time down. So you might find that you've got to read it twice or find extra information on these. Some systems of infinite numbers have minus infinity and some don't. Some systems of infinite numbers have infinitesimals and some don't. Some systems are mathematical fields and some aren't. I'm hoping that you will recognize some of the systems here that you didn't know that you knew. There are many different systems of infinite numbers that have been invented over the years, and I'm going to try going through as many as I possibly can in this short space of time. Part 8 is the final part of this talk, unless I make another part which just includes the highlights or another part which just includes the slides. Observing infinite numbers, systems of infinite numbers, is rather like bird watching. There are a very large number of different types. For parts 1 to 7 of this talk, I didn't require any knowledge of mathematics. But if you're jumping straight into part 8 without reading the other parts, you'll find that it helps to know the following terms in advance. Now, of these, some of them you will have learnt in early high school. Some of them, such as complex number, you won't have learnt until mathematics nearly at the end of high school. And Taylor series, you may need first year university mathematics for that. But in any case, almost all of these you could have learnt from high school, and if you find something that doesn't make sense to you, just leave it out. You'll find that the rest makes sense. You'll find it puzzling how a number can be defined either as a set, a sequence, a series, an order of magnitude, and or a function. But rest assured that it can be. Decimal notation, for example, pi equals 3.1415928, etc., is actually defining a number as a series, 3 plus 0.1 plus 0.04 plus 0.001, etc. For a function, the number can be thought of as the limiting value at infinity. The start of infinity goes back to the ancient Greeks. In particular, Zeno, Aristotle and Archimedes all contributed to the theory of infinite numbers. Aristotle distinguished between potential infinity, which can be approached but never reached, and actual infinity, which can be manipulated mathematically. Now we start to get technical. If you have an application where you need a single value of infinity, with infinity defined as 1 divided by 0 and minus infinity the same as infinity, then a good one to use is what's called the Riemann sphere. Imagine standing on the centre of a piece of graph paper. Allow the horizon to bend upwards like a bowl and continue the bowl upwards until it becomes a huge sphere. The point directly above you is a single value, which is the point infinity. More technically, the stereographic map projection used in drawing maps of the Earth is what is used in generating the Riemann sphere. So a single point on the sphere maps out to a horizon at infinity on a flat surface. Archimedes. Non-Archimedean is a catch-all term for all systems of infinite and infinitesimal numbers. The Archimedean property states that given two positive numbers x and y, there exists an integer n such that n times x is greater than y. Some famous mathematician, I don't remember who, developed a system of infinite numbers based on 1 divided by 0 is not equal to 2 divided by 0. As with the Riemann sphere, we still have infinity equals 1 divided by 0, and infinity and minus infinity are the same. But here we do have higher orders of infinity, because 2 times infinity is not equal to infinity. Wikipedia suggests an application in projective geometry. You will have met up with perspective drawing in art. In 2 dimensions, 2 straight lines meet at a point unless they're parallel. There are systems of geometry where the existence of parallel lines is rejected. So in what's called non-Euclidean geometry, 2 straight lines always meet at 2 points. In what is called projective geometry, we have 2 straight lines always meet at 1 point. If the 2 straight lines are parallel, then they meet at the horizon, a single point at infinity. The equations of projective geometry are the same as those used in painting, in art. The horizon is a line at infinity, and when you get up to higher dimensions, in ND space, you actually have what's called the hyperplane at infinity. Hilbert was a great opponent of non-standard analysis, but Hilbert also invented his own non-standard analysis. In particular, he invented what's called a non-Archimedean continuum. And this is the method that he used. Plus, minus, times, divide. He used to create a field, and he created an extra function here to create more numbers. And the result? It wasn't standard analysis. Cardinal infinity has been studied by very many people over a very long time. I'm not going to go through this too much. Define what's called LF0 to be the first infinite cardinal number, and we have a power set which is defined as the set of all subsets. The power set has a way of bumping up an infinite number up to a larger infinite number. And in addition to the Aleph numbers, people who work with cardinal infinity also refer to the Beth numbers, Aleph and Beth being the first two letters of the Hebrew alphabet. Cantor, in his original paper on cardinal and ordinal infinity, came up with a system where 1 plus infinity equals infinity, but infinity is not equal to infinity plus 1. So we say that because 1 plus infinity equals infinity, we say that cardinal's infinity is shift invariant on the left, because it's not equal there, it's non-shift invariant on the right, and because 1 plus infinity is not equal to infinity plus 1, it is non-commutative. So, relatively few mathematicians have studied this, but it has actually been studied in considerable detail. Modern mathematicians who use cardinal infinity have their own ordinal infinity, which isn't exactly the same as what Cantor proposed, despite what they might say. They say infinity equals infinity plus 1 equals 2 times infinity equals infinity squared, but is not equal to 2 to the power infinity. So as you go from infinity 2 to the power infinity, you're generating a new infinite number. This type of infinity is not a mathematical field. It's not closed under the operations of plus, minus, times, divide. The smallest infinite number is omega. Negative infinity does not exist. Infinitesimals do not exist. Practitioners of cardinal infinity like their proof that the smallest infinite ordinal number is omega. Non-standard analysis allows infinite numbers smaller than omega. So how is this discrepancy resolved? Well, I've written down their proof in slightly shortened form. Essentially, omega is greater than all the natural numbers, but omega is the smallest number that is greater than all the natural numbers, so there cannot be any infinite number less than omega. A counterproof to that is that the set omega can also be written 0, 1, 2, 3 up to omega minus 1, omega minus 2. And this is used in non-standard analysis. This could, in fact, be considered the foundation of non-standard analysis. The value omega minus 1 cannot be finite, and omega minus 1 cannot equal omega. So omega minus 1 is an infinite ordinal number less than omega, and so omega cannot be the smallest infinite ordinal number. So we have here two proofs. One says that omega has to be the smallest infinite number, and the other says that omega can't be the smallest infinite number. Taken together, we actually find that it reduces to a tautology. That is, omega is the smallest infinite number if and only if we assume that omega is the smallest infinite number. The statement remains in the theory, but as an axiom, not as a theorem. In calculus, the statement dy dx means an infinitesimal change in y divided by an infinitesimal change in x. And here's an example. Solve dy dx equals x over y. We multiply by the infinitesimal y times dx to get, which ends up as a hyperbola. Poles in complex analysis and Laurent series. Consider 1 over z minus c, where z is a complex number and c is a constant. The value of c is called a pole of 1 over z minus c, a place where things go haywire. The Laurent series, invented by Pierre-Alphonse Laurent in the year 1843, is defined as the sum from minus infinity to infinity of a constant, which depends on n, times z minus c to the power n. Reverting this back to real numbers to tie this into something you already know, if you've done first year university, that is, a Taylor series. The Taylor series is the sum from n equals 0 to infinity of coefficient times x to the power n. If we extend that down to n equals minus infinity, a to the power n times x to the n is a Laurent series. In Laurent series, we can treat the series as a number. And for each value of n less than 0, it's treated as a different infinite number. Here, minus infinity is different from infinity, but there are no infinitesimal numbers. And we're getting more technical again. The Levi-Civita series is defined in this way: the sum of a coefficient times an positive infinitesimal to a power, and includes numbers like 7 times an infinitesimal, infinitesimal squared, square root of an infinitesimal, e to the exponential of an infinitesimal, addition and multiplication. The Levi-Civita series form an ordered field, i.e. the mathematical operations plus, minus, times and divided by work in the same way on these infinite numbers that they do on the real and rational numbers. Order of magnitude. The function x squared tends to infinity with increasing x more rapidly than x does, and x cubed more rapidly still. So we can write out order of magnitude of 1 is less than order of magnitude of log x, less than order of magnitude of x, less than order of magnitude of x squared, x cubed e to the power x. And going the other way, the orders of magnitude progress downwards towards infinitesimals. In computer science, this is used to classify algorithms according to how their runtime grows as the input size grows. A germ in mathematics is a simple representative object in an equivalence class that captures their shared properties. For example, x, x plus 1 and 2x all have the same order of magnitude. So we say that x is the germ of the equivalence class and write it as order of magnitude x. One way to distinguish between different systems of infinite numbers is by what I call resolution. I've listed various infinities by coarse to fine resolution here. For the finer resolution, infinitesimals, 1 on infinity, exist. For the coarser resolutions, infinitesimals don't exist. Infinity plus 1 is greater than infinity at the fine levels, but then as I go up, the largest term rejects components that are minuscule compared to the largest component. So 1 is minuscule compared to infinity, so the largest term rejects that. Order of magnitude accepts multiplication by infinity as a new level of infinite number, a new order of magnitude, but doesn't accept multiplication by a constant. And cardinal infinity accepts the power set 2 to the power infinity as greater than infinity, but doesn't accept multiplication by infinity as increasing the magnitude. Standard part plays a large role in Abraham Robinson's proof that what is true for real numbers is also true for his hyperreal numbers. It's the finite component of a number and rejects both infinitesimal and infinite components. In part 6 of this talk, where I talked about divergent series, I was able to show that the standard part for this is equal to 0 if x equals 1 and 1 over 1 minus x otherwise. And this agrees with the Taylor series. Now let's just have a look if x equals 1. If x equals 1, we have 1 plus 1 plus 1 plus 1 plus 1 plus 1, which equals omega. And rejecting the infinite component omega, we end up with 0. There are many different types of series. Taylor series is less restrictive than Laurent series. Laurent series is less restrictive than Levi-Civita series, which is less restrictive than Hardy-L series, transseries, and eventually Hahn series. It can be quite difficult to know whether a particular number is a member of a particular series or not. There are some functions that don't follow the hierarchy. So I showed in part 5 of this talk that the smooth half-exponential function, defined by function of x equals exponential of x, can be defined using a sequence of Taylor series by the solution of n equations in n unknowns, but that this function is missing even from transseries. Logarithmic exponential numbers. The mathematician Hahn, who you may know in connection with Riemann, who worked with Hahn came up with the logarithmic exponential functions, and these are known as Hahn-L functions. Addition, subtraction, multiplication and division are what is necessary for generating what is called a mathematical field. The infinite numbers that are logarithmic exponential functions form an ordered field known as the Hahn field and as transseries. Transseries is less restrictive than the Hahn field, than Hahn series, because transseries does allow fluctuation at infinity, but has a system for rejecting fluctuations at infinity to get a unique result. So I've been told. When I first encountered the Hahn series, I gave up in disgust. It looks like it could include everything. However, it turns out to be extremely useful, and it is extremely old for that usefulness. To understand Hahn series, start with the Levi-Civita series. That is the sum over members of the rational numbers. Remember, rational number is something like 3/5 of a constant times an infinitesimal to a power. To get from Levi-Civita series to Hahn series, we replace the infinite ordered set of rational numbers with any ordered set that obeys the normal rules of plus and minus, and they don't have to obey the normal rules of times and divide. That means that gamma, which is what this symbol is an ordered field. Is an ordered group. It isn't necessarily a field. A field requires multiplication and division. The Hahn series is extremely useful because it ties in closely with both Conway's surreal numbers and Robinson's hyperreal numbers. Conway's surreal numbers. Almost all of part 2 of this talk was about Conway's surreal numbers, so I'm just going to give a very quick overview. The Dedekind cut, named after the mathematician Dedekind, can be written A bar B, where A and B are sets, and every element of A is smaller than every element in B. Set containing nothing is called the empty set. The vertical line, the bar, is just an arbitrary symbol used to keep the two sets separate. For any two numbers, x and y, we define addition that way and multiplication that way. Here are some examples of surreal numbers. 0 is empty set bar empty set. It's got nothing. 1 equals a number greater than 0. Minus 1 is a number less than 0. 2 is a number greater than 1. 1/2 is a number between 0 and 1. 1.5 is a number between 1 and 2. Omega is the set of natural numbers, and here I start these at 1. Omega minus 1 is the number which is less than omega and greater than all natural numbers. 1 on omega is the number which is greater than 0 and less than 1 on n for all values of n. Omega on 2, we start at each end. We start at 1 omega minus 1, and then 2 omega minus 2, 3 omega minus 3, and eventually they'll collide in the middle to get omega over 2. Also included in the surreal numbers are all the real numbers, as well as square root of omega, omega to the power 1 on omega, and what is called tetration. Omega, omega to the omega, omega to the omega, omega, which is very large, very fast. In Robinson's hyperreal numbers, each number is represented by a sequence, an ordered sequence. Numbers are added and multiplied term by term. For example, pi plus e can be represented as follows. The subtlety is that if you subtract one ordered sequence from another, or divide one by another, the result isn't always ordered. If you do this with two infinite ordered sequences, it has been proved that the result always contains an infinite ordered subsequence. What is called a filter is used to select one such subsequence that is infinite and ordered, and this becomes the new number. Robinson's hyperreals are enormously successful. Every integer, even an infinite integer, has a unique factorization. Robinson proved in the 1970s that his hyperreal numbers are equivalent to Hahn series. And it has been proved, and I read this in 1987, in a 1987 publication, that the field of surreal numbers is a field of Hahn series in which the ordered set gamma is equal to the surreal numbers themselves. So the surreal numbers define themselves. Technically, this only proves that the surreal numbers are a subset of the hyperreal numbers, but I know of no counterexample to the hypothesis that the surreal numbers are identical to the hyperreal numbers. Which infinity at a glance? This is sort of like the table you might find if you're buying a product and wish to decide which product you want. I'll start at the bottom. Hahn series surreal numbers and hyperreal numbers may be identical. They have the same resolution, which means that if I add an infinitesimal number to an infinite number, the result is different to the original infinite number. Each of them contains the half-exponential function, and each of them is an ordered field. When we go back to Hardy series and transseries, the half-exponential function, that is the function such that function of a function equals exponential, is missing. Standard part, largest term, rejects smaller components, and that means that the largest term is actually missing, is actually not an ordered field. Because, anyway, similarly, order of magnitude is not an ordered field, and order of magnitude also misses minus infinity. Levi-Civita series is an ordered field, but Laurent series is not. Infinitesimals exclude infinity. Shift-invariant ordinals, cardinal or Cantor's ordinals and cardinal infinity are all part of standard analysis. Hilbert's version of the Veronese continuum also has fine resolution. There's also a field. Perspective drawing, also known as projective geometry. Well, not much we have on that. 2 divided by 0. I call it here the biggest infinities, but infinity equals minus infinity. And the Riemann sphere has no resolution because there's only one infinity. Non-Archimedean includes all of the systems of infinity in this table, as well as some systems that aren't infinite. If you want to look this up, and I don't recommend it, non-Archimedean also includes what's called the p-adic numbers. But feel free to forget that. I wanted to try to explain how some system of infinities can be seen perhaps as subsets of other systems of infinity. So for instance, Laurent series are a subset of the Levi-Civita field, which are a subset of the logarithmic-exponential numbers, which are a subset of Hahn series. This little star here is what most people think of when they think of infinity. But there is a very wide range of infinite numbers and infinitesimals that aren't what most people think of as infinity. But these are all different types of infinite numbers and infinitesimals. Take-home messages. The famous proof that says that omega is the smallest infinite number has a counterproof that says that omega can't be the smallest infinite number. Taken together, we can see that omega is the smallest infinite number if and only if we assume it to be the smallest infinite number, and vice versa. This guidebook includes very many different ways that have been used to construct systems of infinite numbers. The most complete systems of infinite numbers are the Hahn series, Robinson's hyperreal numbers, and Conway's surreal numbers. This is part 8 of the talk. There are 8 parts in all so far. I have no plans to add extra, except for putting all parts into a single presentation, slides only with no commentary, which I might do later. This whole presentation is based on a paper that I wrote back in the year 2011, which was published as 2 papers on archive. These 2. The YouTube videos for the 8 parts are as follows. I've talked in more detail about some of the different systems of infinite numbers in earlier parts of this talk. The non-shift invariant ordinal infinity is used in all parts. Naive infinity you'll only find in part 1. Part 2 contains Conway's surreal numbers in much greater detail. Parts 2 and 7 also include information on Robinson's hyperreal numbers, and the new limit on the sequence is mostly found in part 3 and in part 6. Part 6 being the talk on divergent series. And here is something, if you ever want to delve deeper into this. Wikipedia is a good source for many of the topics raised in this paper. If you don't understand anything that you read here, try Wikipedia or Wolfram Alpha. That's pretty good too. But there are documents, some of which are available on the web, some of which aren't, about such topics as surreal numbers, orders of infinity, hyperreal numbers, Cantor's ordinal numbers, the Veronese continuum, divergent series, renormalization, and paradoxes including infinity.